Sure.
So today our presenter is Sheikh Mohammed Mahmoud Al Islam from University of Dhaka and also working with Duke University in USA. Over to you, Professor.
Yeah.
Thank you.
Thank you so much. Yeah. Thank you for the kind introduction. And it's absolutely my pleasure to be here today. And today I'm going to talk about Earth sensing at the human microwave frontiers, mostly focusing on non-contact radar-based identity authentication system. So, for my today's talk, basically, I have those agendas in my slides. First, I will start with the basic introduction of Doppler radar-based non-contact physiological monitoring. Then I will talk about the basic principles, how this particular technology works, more specifically for vital signs monitoring. And then I will talk about the research project work that I have already done with the identity authentication system and the associated challenges of this particular technology and outcome and what are the a future direction. And then I will conclude my talk. So basically, this particular workshop series is focused on AI for microwave sensing. In my particular work, what I did basically using the radar technology, we can track like different vital signs such as like breathing rate, and heart rate variability. Different vital signs information can be basically extracted. And whenever we extract those type of signals, it's basically the in phase as well as the quadrature phase channel waveforms. And from there, we try to extract some meaningful information that carries both valuable informations, and then we feed them to the machine learning, or we can also do directly uh, the deep learning model to extract like a meaningful information, and from there we try to find some particular purpose, for example, the identity authentication or sleep posture recognition, different aspects we can like focus on. So the one of the challenges basically I will talk about during my whole presentation, that there are few challenges as well as like how AI can help to overcome those challenges, as well as like how we can leverage RF sensing with the AI web, with the RF sensing with the AI technology, so that we can come up with some smart technology or smart sensing technology. So my core message of this particular talk would be AI does not replace the radar physics. Basically, we need the radar physics, but AI can be basically one of the potential tool to make those RF sensing more smart, as well as that can provide like more clinically meaningful informations. All right. So to start with my talk, basically, non-contact vital sign monitoring using microwave Doppler radar has shown great promises in healthcare application and has become an active area of research and study uh, for for about 2 decades. So non-contact vital sign monitoring using microwave Doppler radar has shown great promises in healthcare application, has become an active area of research and study for about 4 decades, with proof of concept demonstrated for various applications. And there are several potential advantages. It's a non-invasive, it's a wireless technique, no wiring need to be attached to the body. Definitely, it's a very comfortable technique. As I said, it has several potential applications. It can be used for sleep apnea, if you are familiar with the sleep apnea, because sleep apnea patients need to wear a lot of devices, which is basically can create some burden to the patients. It can also be used for sudden infant death syndrome, because infants cannot put the respiratory monitoring devices on their chest surfaces. It can also be used for burn victim patients for monitoring their vital sign. In this particular project work, basically my focus is on security government application, and it's also related, it can be also part of the occupancy, like counting the number of people in a room environment. So I will mostly focus on my talk on this particular application areas, more specifically the top one, the security and government application. I will try to focus because my talk is totally like dedicated to that particular application. All right, so how this technology works, I'm not sure like how much you are familiar, but this technology particularly works is very similar to the Doppler shift or It's very similar to the how police basically measure the velocity of a car. So basically, radar sends an electromagnetic signal towards a human or towards human chest surface, and when the signal is being reflected, basically its phase changes, and the phase change of the reflected signal is directly proportional to the tiny movement of the chest surface due to the cardiorespiratory activities. And it's very similar to, as I said, the frequency shift. But for the period, as the chest has we are tracking the cardiorespiratory motion. So it's a periodic displacement. So what we are getting, basically, we are getting the phase change information from the reflected echo. And from that phase change information, basically, we can extract variable informations and a lot of valuable informations. For example, the breathing rate, for example, the heart rate. And I'm going to talk about like how those information can be extracted from the radar reflected echo. So So as I said, this is just like a simple equations. So we are basically transmitting electromagnetic signal through radar, and when the signal is being reflected, basically its phase changes, and the phase change of the reflected signal is directly proportional to the tiny movement of the chest surface due to the cardiorespiratory activities. And from that phase change information, we can extract like different vital signs such as breathing rate, heart rate variability, airflow profile, breathing depth, and a lot of other informations. So if we look at using some simple equation, you can see that transmitted signal can be represented as a T, and where A is the amplitude, F is the frequency, feet is the phase noise of the oscillator, and phase of that particular transmitted waveform. When the signal is being reflected, basically you can see that the phase change equation is coming here. So from that phase change information, let's say we have like a quadrature radar. When the signal is being reflected, its phase changes. So we can get the phase modulator signal at the receiver. If it is a quadrature channel receiver, basically we get the two channel signals. One is in phase, another one is a quadrature phase, and you can see this is basically the typical Doppler physiological radar module. Or if you buy any kind of module that consists of those type of typical RF signal processing chain. So in the output, basically we got the in phase baseband signal. That's the in phase. You can see that is represented here BIT. So D naught is the distance from the radar transmitted antenna to the chest surface. XT is the chest displacement information, and del phi t is the delta phi t is the basically the phase noise of the oscillator. And when the signal is being reflected, as I said, if it is a quadrature radar, we can get the two different type of channel signal. One is the in phase, another one is a quadrature phase channel signals. And from those in phase and quadrature phase channel signal, basically we can extract like a IQ waveform. So quadrature, like you can see that this is an I in phase channel signal and quadrature phase channel signal, and from there we can basically plot an IQ plot. If the signal is coming from the periodic motion, as I said, we are basically tracking the tiny movement of the chest surface. So, and that's the periodic displacement. So if the signal is coming from the periodic portion of that particular target, then we can get an arc, and periodic motion basically forms an arc. And from that periodic motion, basically we can estimate the center as well as we can estimate the radius of that particular arc. So that also helps us to understand like whether signal is coming from the other portion of the body or any kind of random body movement can also be detected. So from that, analyzing that particular IQ plot, basically, when the motion is periodic, we get like a fixed point radius. Fixed point radius is maintained, and if the signal is coming from the any kind of like sedentary respiration, basically, we can get a steady radius, and then from there if there is any kind of like a fluctuation, you can see this is a basically steady radius. If there is any kind of random body motion, basically that particular radius or fixed radius cannot be maintained. And extracting a ray during like a random body motion or any kind of like a, it's not like a meaning, it cannot provide any clinically insightful information at all. So now the question is like, now we understand like from the IQ plot, basically we can extract the breathing, you can understand the which particular signal is coming from the periodic portion of the body or periodic movement. So uh, to extract the breathing rate, basically you can see here, this is the in phase and quarter phase channel signal, and we do the like a demodulation. There are two different type of demodulation is mostly used. One is called the linear demodulation, which is very similar to the principal component analysis. Another one is a arterial demodulation, and from there we get the maximum chest displace information by combining those two channel signals. And if we do the as you know that breathing rate and heart rate, they are basically the harmonic of each other. And from that chest displacement information, if we do the filtering to basically isolate those particular band and then the FFT, first Fourier transform, basically we can extract the breathing rate as well as we can also extract the heart rate related informations. And this is one of the paper I already put on the slide. If you are interested on this particular technology, this is the one of the first paper related. This is one of the like a not first paper. I would say this is one of the like a most popular article on this particular in terms of to understand the basics of this particular technology. All right, so the one of the particular question comes whenever we are using the radio frequency sensing or radio frequency signals, how to isolate the random body motion. You can see here the green portion is coming from the breathing, and this particular random motion or the is coming from the limbs. So we can do the IQ, we can test the IQ plot, and from there we can understand that the signal is coming from either periodic portion of the body or it's any kind of like a random body motion. We can mitigate, we can do the periodicity test to eliminate those like a random body motions, and we can just focus on the that particular periodic portion of the body informations, and from there we can do the bandpass filtering to isolate the breathing rate as well as the heart rate related informations. So in my particular identity authentication system, I did basically this was my one of the PhD research I worked on. So we are trying what we are trying to do. We know that the traditional authentication system is like a fingerprint is one of the most popular, as well as facial recognition is now a more one of the established technique. But all of them basically needs like a contact, especially and it's not like a continuous. So in my PhD research, basically I was focusing on whether a radar can also be used to recognize people from their cardio displacement informations. So if I found that like whenever I was doing my PhD, I was looking into this problem, and I found already few papers were published where they were attempting to recognize like a single participants. That means the data was collected when one participant was present in front of the radar system. And my research question during that time was to like focus on, can we use at least like two participants, because in realistic setting you know that when there are two subjects present in front of the radar, basically radar gets a combined mixtures of the two different respiration patterns, right? So as I said, like my focus was the let's say airport security system or sleep apnea testing or automobile industry. There is a high chance of presence of two subjects. So how to isolate individual respiration pattern from their combination mixtures? And from there, I try to find some important digital biomarkers to recognize peoples. And I'm going to talk about like what are those biomarkers and how machine learning is basically like integrated with that particular biomarkers to recognize peoples. All right. So this was one of the my earlier research question when I started my PhD, and I tried to like come up with some solutions to basically move forward this particular technology in terms of like implementing this technology in a realistic environment where there is a high chance of presence of two subjects in front of the radar system. All right. So I know like many of you may be familiar with a beamforming or like a beamforming as well as like a beam tracking. So or like a you can also you can see that radar has a beamforming capabilities if it is like a MIMO radar, multiple input, multiple output radar. Basically, it can switch beam in different directions. And radar has a certain like a spatial limit. So that means like let's say radar has a like a 30-degree beam width. So it can track, let's say when there is a two subject, if they are isolated in a like a sufficient distance, then radar can basically use the direction of arrival or angle of arrival informations to understand the particular subject position. And I'm talking mostly in my presentation related to continuous wave radar. I know many of you may be working with the FMCW radar as well as the ultra wideband radar. But my PhD study as well as my research group at the University of Dhaka is mostly focused on CW. We are also working on FMCW, and the results I'm showing for mostly for continuous wave radar. And let's say when there is two subjects present in front of the radar system, let's say they are within the beam. And when they're within the beam, still radar can track their informations, or radar can basically use the angle of arrival informations. But if they crosses that particular certain limit, that's the minimum resolution limit, then radar cannot like use the angle of arrival informations. So in home apnea, sleep apnea study, there is a high chance of presence of two subjects. Let's say when there is a two subject present in front of the radar system, as I said, radar can get a, like a combination of mixtures, as well as beamforming will not work if they cross a certain resolution limit. So for my particular project, basically I focused on home sleep apnea study data sets, and we collected those data sets. And we come up with this particular technology can be viable, especially for there is a very common trend in US that people try to do like a data falsification, because if they are diagnosed with like sleep apnea, they may lose their potential job, as well as there is a high chance of their increase in their insurance premium. So a previous radar was used for the unobtrusive like a sleep apnea testing. And in my case, I was trying to use the radar for identity authentication, so that like a sleep apnea testing can be more secure, and it can also be done in a home environment. All right. So for sleep apnea, polysomnography is one of the like a common technique. I know many of you may know what they need to do like during this testing. Like they need to go to the hospital, and they need to spend like a certain sleep laboratory, and it's like a very complicated process. Instead of like a polysomnography, if you can use radar, basically radar can do the those type of tests in a home environment without attaching any sensor to the body. So there is like a lot of advantages. There is a no sensor burden technology is needed. So in my particular work, I try to show like a different scenarios. Let's say like there is a presence of two subjects, how to isolate those individual respiration patterns. I also come up with some particular technology or mascot system that can help to prevent like eavesdrop, as well as the spoofing, to hack like a that can remove the hack wireless channel, as well as the that cannot inject any kind of like a false data. So my talk or my proposed technology will be focused on secure radio-based identity authentication, that is consist of like a secure protocol, as well as it can be used for like a in-home sleep apnea testing. So as I said, like one of the challenge I try to solve is the like a mix-up. Mix-up means when there is a presence of two subjects in front of the radar system, and if they crosses that certain angular resolution limit, what technology or what particular algorithm can work? So I developed an algorithm that's called SNL-based intelligent decision algorithm. And if you're interested, you can get this paper in IEEE that is already published. I already provided those references. So basically, what we did is very similar to the handoff decision algorithm in a mobile cellular communication. So what we did basically, we did the simulation. Let's say two subjects are present in front of the radar, and if it starts like cross a certain resolution limit, and this is definitely for short range sensing, how their SNR changes, and if they are within the beam, and if they are crosses that particular beam width limit, what about the SNR, signal to noise ratio? If SNR has like a certain, and we come up with some SNR lookup table, and if SNR crosses with a certain limit, then we use the independent component analysis JED algorithm. If if their phase difference is within certain limit, that can help them to uh, distinguish using the direction of arrival estimation. So basically, what I did, I come up with some intelligent way so that we can use both ICAJ as well as the direction of arrival, and in that way, we can track the people if they are within the beam or if they crosses that certain beam with limit. Still, we can like monitor them. So this was the experimental setup that was done at the University of Hawaii. So you can see here when there is a two well-spaced subjects, this subject can be basically separated using the direction of arrival estimation. And initially we did this experiment in a anechoic chamber to understand their signal to noise ratio as well as the signal's quality. But later on we also employed this particular system in a like outside environment as well as we did some clinical study as well. All right. So this is one of the results you can see here. Let's say two subjects are well spaced. What I'm showing here, blue line basically represents the I1 channel and red line that represents the Q1 channel. And if they are well spaced, let's say subjects are within certain like a beam width, then we can easily find their phase difference between the two different channel signal and use the monopulse radar, and we can basically at that point we can basically switch beam in different directions and we can isolate them, and you can see already see the blue line that basically coming from the radar, and you can see that's basically the breathing rate of one particular subjects, and the red line here basically shows in the effective plot is from the chest belt, which is basically the reference respiration patterns that you got. All right. When subjects are closely spaced, you can see here I1, Q1 in the top plot, and they are basically very messy. And in the IQ plot, you can see, and even the FFT basically you cannot get like a isolated peak or like a single dominant peak here. So uh, at that point, like I use the independent component analysis JADE algorithm. That's basically blind source separation technique. I'm not sure like whether you are familiar. If you are interested, please, you can read the paper. So what it does like from the kurtosis of the like a total signal, it can basically isolate the individual patterns from the signals. And as I said, like this particular work was published in like 2020, so almost like 6 years. The technology has definitely advanced more than that. But at that point, like we were the first study that we did, and we reported using CW radar, and we processed that certain angular resolution limit, and that shows like a very good accuracy. And here I'm showing the if I combine like a both method, like let's say my proposed method is like a hybrid method where I combine the ICAJ as well as the direction of arrival. If I combine both of them, you can see that the black line, which is the hybrid method, that basically supersedes either in direction, because direction of arrival or angle of arrival has a certain resolution limit. It depends on the antenna array spacing limit that either we bought from the company, maybe the on-shelf radar, or maybe like someone, if someone designs the radar, it cannot be like a super, it cannot provide like super resolution. There will be certain angular resolution limit, so at that point, the technology will be like a kind of like a start with that particular angular resolution limit capability. So that's why we need to combine like a both techniques that can make the ubiquitous as well as the both closely spaced subjects and like a well separated subjects can also be isolated. All right. So with that, now we know like how to isolate the individual subjects when they are like a when they are present in front of the radar system, and this particular algorithm helps to distinguish the different vital signs when there is a presence of two subjects in front of, and another important aspect is like it's not limited to certain angular resolution limit. Even if it crosses certain angular resolution limit, the ICJ can take care of that. So then we looked into like a then we proposed basically which particular algorithm or which particular feature can be like one of the potential useful for recognizing people. So we found in the literature that breath ratio means like whenever radar is basically captures, you know that some portion is coming from the inhale, then inhale, exhale. In between there is a transition. So basically, here it contains the heartbeat related information. So this is one of the radar respiration pattern. So in the literature, we found that especially this particular biomarker was basically reported by my group, the PhD student who graduated before me. He reported this particular biomarkers, and it showed like a very good results, more specifically for like a sedentary pattern respirations. And for recognizing people when the people are in sedentary conditions. So what this particular feature does basically, in between the transition, we take four different points. So this is the handcrafted features. And then in the next episode, we also consider the four different points. And that points was selected based on the amplitude of the displacement or the chest displacement information. We took like 30% to 70% chest displacement information and discarded certain portions. And more specifically, this particular method we call in our lab was like a dynamic segmentation. If you're interested, like you can also see this paper, like IEEE Journal of Emerging and Selected Topics in Circular Systems. And from that particular features, using those features for 10 different subjects, it showed like a very good accuracy. Later on, we discovered that when people are doing any kind of physiological activities, let's say someone is coming from gym and they're taking the radar measurements, and someone is like using stairs, and then after certain amount of time, if someone takes the radar measurement, we found that those particular pattern changes, because you know that cardiorespiratory, after some physical exercise, cardiorespiratory breathing rate as well as the airflow profile also changes. So later on, we found some patterns like the inhale and exhale ratio changes. Another thing for this dynamic segmentation algorithm, it doesn't consider heartbeat related information, as we are taking like a 30% to 70% relate 30% to 70% amplitudes, and we are not considering the heartbeat related information. So my task was to come up with some interesting digital biomarker that can be used not only for the sedentary condition, but also let's say people are coming from gym or people are coming from any kind of physical exercise. Can we still have some like a reliable digital biomarkers that can be used to recognize people? And this is, I'm just talking about the most important and meaningful biomarkers. Apart from that, there are other biomarkers we also extracted, and then we feed them to the machine learning. So I proposed basically and another interesting biomarker that is called, using the, I call it like a improved version of the dynamic segmentation algorithm. So, and before that, you may ask this question like why radar can be used to recognize people. So it has been proven in the literature and in the medical science that different people have a different breathing patterns, as we are tracking the chest displacement information. So it's exploratory. It's not like a mature technology, as I should say. It's a kind of like a exploratory research, and a lot of research is going on whether the cardiorespiratory signatures or cardiorespiratory pattern can be way to recognize people. So as I said, like in the literature, there has been like a clearly a lot of literature is there where it has been reported that breathing pattern diversity related technology is there where that can be used to recognize people. That's what we explored in our research. Anyway, so as I said, this is one of the potential limitation of the dynamic segmentation, as it didn't consider the heartbeat related information. So what I did basically, I tried to uh, improve this particular dynamic segmentation algorithm. In the right portion, you see the previously reported dynamic segmentation algorithm, and in the left portion, this is my improved version of the dynamic segmentation algorithm. Where what I did basically, I used the triangulation method because I said dynamic segmentation didn't consider the peak information. So it's basically missing the heartbeat related information. What I did basically, I did the triangulation, and then from there, I didn't use the trapezium, rather I used the triangle episode by episode. I did the three different points. You see that this is the like maximum peak and the minimum two peaks. I constructed the triangle using this inhale exhale episode. And in the next episode, another, it consists of like a two different peak points, and another one is like a another like a minimum points. And in that way, I took the average inhale exhale area ratio across the like captured radar waveforms. All right. So if you're interested, like you can also read this particular paper in the that has already been published in IEEE Transition on Microwave Theory, and that the DOI has also been provided in my abstract of the talk. All right. So this particular hyper features shows like a clearly like a lot of meaningful information. What I'm showing here, we did this study for 20 different participants, and we collected those data like a more than for 6 months, and we tested those like a whether this particular, and we found that this particular features or this particular digital biomarkers, you can see the subject one. So this is the inhale exhale area, then exhale inhale area. In that way we took the area ratio across all those participants. So another question may come up in your mind, that what does it mean? Basically, this particular area ratio shows like how one initiates the next cycle of respiration pattern. Let's say I'm taking my inhale, then exhale, inhale. So within that episode, how one starts the next, or how one initiates the next cycle of respiration pattern. So that was kind of like a represented here by the inhale exhale area ratio. All right. So we did this study for more than 6 months for 20 different participants. We collected those radar waveforms. We also took the participants if they're coming after gym, like how those pattern changes, and then we took those we collected those 6 months data set, and we took the 60% of the data set for training and 40% data set. We extract not only the I was talking about spent like few more slides talking about what was the meaningful digital biomarkers, but apart from that we also extract the breathing rate, heart rate, breathing depth, airflow profile, and other like trivial features, and then feed them to the machine learning. And we found that the quadratic SVM that outperformed than other classifiers with an accuracy of almost like a 96.5%, as well as others like other machine learning the classifiers. This is just I'm showing the trivial one, and this is one of the like a quadratic SVM classifiers. Basically, the confusion matrix, and you can see for few participants we found, as I said, like it's not very accurate, and we are using like a 6 months large scale data sets. So, and it contains like sometimes the physiological activity that we found like some discrepancy, and especially for few participants there was like a close matching in their inhale acceleration area ratio, but still it shows like a reasonable for a lot of participants, it shows like reasonable performance. That's why the overall accuracy, classification accuracy, almost like a 96.5%. So then we did this comparison with the state of the art, and you can see that this was the first reported results where we tried to demonstrate that this particular technology can also be implemented for at least two subjects. And that particular paper is already published in the IEEE Transaction on Microwave Theory. And if you're interested, you can look into this particular paper, and feel free to knock me if you have any questions regarding this particular work. All right. So as I said, like one of my goal was to implement this technology in a sleep apnea. I will take like a 5 more minutes to wrap up my talk. So we try to implement this particular recognition system in a clinical visit. Like, can we make this technology? That's the goal was to remove the burden of polysomnography. So let's say I developed a modality switch compliance tracking system. So that was consist of like both the millimeter wave radar as well as the chest band waveforms, and the basically the chest band sensors, and then like how to use the tracking system from the apnea app, and we developed those app, and we come up with how to make those technology like a more compliance, because people are like a kind of afraid doing this test in a clinical settings, and it's a very expensive, almost like $1,000 per night study. All right, so Chessband basically provided us the bootstrap shared key, and that from that breathing pattern, we come up with some cipher text, and we upload those cipher text, and we wanted to make sure that radar and as well as the chest band, there can have like a tracking system so that that can also be implemented in a in-home sleep apnea study. And we wanted to make sure that no data falsification can take place by developing the modality switch compliance tracking systems. And that paper is already available in IEEE Internet of Things channels. If you're interested, you can also look into that paper. And as I said, the modality compliance switching system basically uses the third-party key evaluation protocol. That's basically a combination of the fuzzy commitment scheme as well as the error metric that is related to Hamming distance. And from there, we try to basically from the fingerprint, we call it like breathing fingerprint. So we use the Reed-Solomon encoding function as well as we come up with the key derivation function so that no one can basically like inject any kind of other data. So that, as I said, like one of the concern of those doing this type of clinical study in a home environment, people may change their or people may falsify their results by putting like other people on the apnea test so that they may not like diagnose. The goal is because they do this because they may lose their potential job if they were diagnosed with like sleep apnea, especially in US. It's a very common. So, as I said, the breathing fingerprint, we looked into the breathing finger. We basically what we did from the radar signal, from the breathing pattern, we convert those breathing pattern, radar waveform into the binary representation, and that was used as a breathing signatures for each participants. And we also look into their Hamming space for one participant. If it is similar, basically we preserve that particular uniqueness. If it is not similar, then Hamming distance was one of the like error metric for that particular. And you can see here, this is one of the representation what I try to see. Let's say this is the radar waveform and it's like a 3-point algorithm. If it crosses certain threshold or certain amplitude threshold, we provide the code 10. If it crosses like a, let's say in the lower limits, got a certain amplitude limit, we keep the code as a 01. And if it is in between the Q plus and Q minus, basically we provided that. But in that way, we try to make it like a secretive as well as the people cannot replicate the breathing signatures of each participant so that it can also be stored in a clinical setting as well as this type settings can be like a more like a robust as well as the more basically secure. All right. So this content was basically proposed by us, like my our group. Um, and you can also see those like papers, IEEE Microwave Magazine already published, and as well as the IEEE Internet of Things journal, as I said. This is one of the implementation of the proposed Masco system. That is we did this study in a outdoor settings to see whether RF propagation being affected or whether we can do. And as I said, like we tested not only for the like two subjects. This is one of the scenarios. We also try to generate some scenarios where other people breathing pattern was injected into the system, and can our system basically track those injection and just extract the meaningful informations. All right, so this is just the performance of those particular breathing fingerprint as well as as I said, we did the analysis. All right, so just before wrapping up my talk, is already I crossed the time limit. So in key takeaway, basically Doppler radar can capture respiration-induced micro motion, and one of the potential benefit, if you look at the wearables like the smartwatch, on the potential benefit of this technology is a non-contact, so you don't need to wire any sensor to the body. So that's one of the like a selling point, and people are getting interest because of this particular non-contact modality of this particular sensing technology. And as I said, like I showed some breathing dynamics related information and how to extract. And as I use the just the machine learning, so I have to use some like a handcrafted features. But with the current deep learning architecture as well as different encoder, you don't need to do any kind of like a handcrafted features. But handcrafted features can provide, I would say, some more clinical information. That's what I was trying to show. Um, if I extract the inhale exhale area ratio, what does it mean in physiological point of view? And we need like a hybrid signal processing as well as in the future work, robust AI, how to use like a multi-radar fusion as well as the how to make those system like a more efficient. let's say if we want to implement those system in a realistic setting, there will be a lot of episodes when people are like walking, when people are like moving, how to come up with some or how to integrate AI technology to address those challenges so that this particular technology can bring into the real world, so that the goal is not to basically replace the traditional fingerprint. This is one of the like a one of that this is, would be one of the like a way where we can start with the fingerprint. Then let's say you enter into the airport and you are like tracked by your breathing pattern using radar. In that way, the technology can be like a more robust, because currently the technology is limited to using the one point entry system, and then there is a no authentication at all. So a lot of like a data falsification, then data like a manipulation can also be happen. All right, so I hope like this particular talk focuses basically on the non-contact RF sensing related identity authentication system and how that can be leveraged to the machine learning to come up with some like a clinical as well as some insightful informations. All right, so this is just like my research group and my collaborators. The top like a figure or top like a photo you can see is my in my office at the University of Dhaka in Bangladesh. Currently, I'm a kind of like only from my position, I'm doing my postdoctoral research at the Duke University in North Carolina. So basically, I'm like grateful to my collaborators, my students, my researchers, because the results what I've shown, like my PhD work, especially I'm with the at the University of Hawaii, I did the work. So yeah, with this, I would like to conclude my talk and thank you again for inviting me for this particular talk. Thank you so much.
Thank you, Dr. Islam. Really nice talk and very informative. The
Thank you
floor
so
is
much.
open to questions. Anyone with any questions, either you can drop it into the chat or you can just unmute yourself and straight away go with your question.
Hi, thanks, Dr. Sayed, for arranging this kind of informative talk. I have a comment plus a question. And so you are monitoring some vital health signs using the radar. So I was just wondering, what do you see the future of like radar technologies for biomedical applications? For example, can we do some like blood test with the radar? I mean, just can we find out what is the composition of the blood or chemical composition of blood like this? So we don't need to like get blood out of the patients and then do the testing. So can we do this using radar in future, or what are your thoughts on that?
Thank you. Yeah, that's a great question. Yeah, so this particular, so your question is, first question is how this technology like moving forward so far. I would say, yeah, for different application, it already like proved its efficacy. As I said, it's a non-contact, even though like there are a lot of challenges. For example, like for obstructive sleep apnea, OSA, this particular technology has done like a lot of like clinical study, and I know like a few other uh, companies are there who are already using the radar for vital sign monitorings. So it has like a using for, let's say, in automotive industry for monitoring breathing rate and heart rate of a driver. It has also been used in some like a automotive company. So as well as Google has a, like the Google Solid project where hand gesture recognition has been done even in a Google phone. That the switch control is done by through the hand gesture, so that is being tracked by the radar system. So in terms of like from laboratory setting to the real world deployment, it has gone a like a I would say a huge path. So definitely there are progress as well as the challenge, as it is not a, like a mature technology, there are a lot of challenges, which is a good thing as a like a early career researcher, so that we can work on like a different areas. That's a good thing for us. And your another question is, can we monitor the blood composition? As far I know, blood composition monitoring, I saw like a few papers out there. It's a not blood composition, but I saw it's a, like a pulse wave velocity measurements. So you know that let's say signal is coming from the chest, the signal is coming from the abdomen. So in between there is like a propagation delay. So from there, basically pulse wave velocity. So that can be used for the basically the radar based like a blood pressure monitoring technology so that you don't need to wear any device on the body. And I saw people are also trying to use this RF sensor technology for diabetics monitoring, where it's trying to see like a, let's say, blood is composed with some sugar and blood without sugar. Definitely, RF propagation will change, right? The reflector signal properties will change. So people are investigating on this. You can find also few papers where people already started using the RF sensing technology for basically the diabetics monitoring for blood pressure measurements. So yeah, so those technology has already been in an exploratory stage. Like a lot of research papers are coming up, so maybe within few years, we don't know, like there may be some technology where radar is being used for blood pressure monitoring. Radar may be used for blood glucose monitoring. Yeah, that's a great question. Yeah.
Thank you.
Thank you. Before I go to the next question in the chat, I will just like to remind everyone that we have shared link for today's attendance and for certificate. Please make sure that you fill up the form available on the link, and also the quiz for getting the certificate of passing is available in the chat. Please make sure that you complete it. It will be available open till next few weeks. Please make sure you attempt and complete the quiz. Quiz percentage for passing is 40%. Okay, I will just read the question in the chat from Jeffrey. You mentioned some security implementation in your work to avoid data inception and security. Can you please elaborate more on that in terms of cybersecurity? What are the key challenges related to this domain of work?
That's a great question. So in our work, basically, we use the fuzzy commitment scheme. So what we did from the radar captured respiration patterns, we extracted some code word. Basically, it's a breathing code word, and then we transmitted those breathing code word from one device to another device. And whenever we basically extract or decipher those information, basically during transmission we use the like a randomness or fuzziness in the signal. And whenever we are capturing on the decoding portion, basically for each participants, we use some code word that we know from the transmission side as well as the reception side. So in that way, fuzzy commitment scheme was basically implemented, and our goal was not directly using this for cybersecurity, but definitely I can clearly see there is a, like a pathway to implement this technology for the cybersecurity or related structures. So in our case, after the breathing dynamics capture, basically we try to use some code word, and then we wanted to make sure those code word can also just be extracted like a other related devices based on the code, not by other cannot like decipher those information. So it's related to very common scheme that we call the fuzzy commitment scheme. And for the code word, we developed the code word by ourselves. I showed like how to come up with like a, let's say if it crosses certain limits, and then this code word within certain limit, this code word. In that way, like we try to show the potential of this technology for making it more secure, but definitely other techniques can also be integrated. And you can like get, mm, as I said, like in my presentation I already provided the paper link. If you're interested, probably, yeah, so you can integrate like a other cybersecurity related techniques there, so that the, yeah, definitely it would be like a more interesting as well as it will be more secure, more robust for sure.
Great. Let's quickly move to the next questions because I can see a couple of questions. Let's try
Sure.
to be short to respond. From Neza, there are two questions. First one is in comparison between CW radar and FMCW radar? Why did you not also take UWB radar into consideration?
Yeah, so whenever I was doing my PhD, my lab was focused on CW radar. Then we also switched on like FMCW radar. CW radar has an advantage in terms of like signal processing chain. You need like a fewer more steps. And as you are tracking the chest displacement information is a periodic, CW can provide valuable information. As I said, with that, CW cannot get the range information. So you need like other signal processing approaches. For example, I use the ICH8. So yeah, there are like trade-off, but definitely FMCW has a lot of advantages than CW radar. But as well as CW has like a simpler architecture, signal processing chain is simple. Yeah.
Great. Next question from the same person is, are you working on cases where there is an obstacle, barrier between the people and the radar, or not yet?
Yeah. We already, if you look at my group, we already published few papers where we also use the through the wall human, like a breathing rate and heart rate recognition. And we already addressed those. And it's still, I would say this technology is still under exploratory, where let's say during like any kind of disaster search rescue scenarios, whether we can find the trapped person from the under the debris. So yeah, we already explored, and it's a RF propagation becomes more challenging when wall is present in between the human. Yeah, so we
Great,
already addressed. Yeah.
great. Next question is from Khatija. Um, just about the data fed to AI model, how did you collect it?
Uh, the data collection, as I said, like lab needs to have a like IRB protocol. So any kind of clinical study or anything, you need to have IRB protocol. Initially, we start with the anechoic chamber, and then we can do that like in an office environment and everywhere we can use those type of radar system. Yeah, so you need IRB protocol with the that particular lab, and then you can do the clinical study for or like at least the pilot study for publishing any paper.
Great. The next question is from Mohammed. The radar used in your projects, what was the frequency bandwidth? Like which
That's
band was used?
That's a great question. We use the 2.4 gigahertz to 24 gigahertz. So it's just K band.
Okay, great. Another question from Khatija. I have another question about the method based on the SNR. When the SNR is very weak, so the signal is fully covered by the noise. Have you considered these cases too? Like when the
Uh,
noise is
yeah,
high, have you
right,
considered
right, right.
those kinds of cases?
We'll consider those cases, but in our case, we mostly focused on short range sensing because this type of vital sign monitoring, like it's not like a long range sensing. So we consider the short range sensing in a sense like let's say 5 meter or 0.2 meter to until like a 2 meter. But if it goes far away from there, probably the SLR may be much more effective. And we also consider within a certain angular resolution limit. For our case, the radar module we used from it's a KMC4 RF beam radar. So that was has a beam width of like a 30 degrees. So we just consider the short range sensing basically.
Great. Are there any further questions from anyone? If there are no further questions, I think we are pretty much on time. So last chance, if there is any question from anyone. Amna, do you have a question? If there is, just unmute yourself and you can ask straight away. Please go ahead.
I have a question. Do you hear me?
Yep.
Yeah.
Please go ahead.
So what are usually the gain of the antennas you are looking for such systems?
Gain, I would say like a 13 dBi. So gain is not is as it's a short range sensing. So 10 dBi should be fine. Two to let's say in my case, my antenna I can say it was like 13 dBi. Yeah.
Okay. And regarding when you have like two people or something, I mean, in phased array antennas, you can do like, putting null to the person you don't want and just put your beam to the person. So probably you can do such things to distinguish between many people.
Right, right. So you mean the nulling the beam width? Yeah, yeah. In our case, we use the on-shelf radar. So what we did basically, we try to use like two different approaches. And when the angular resolution limit crosses that limit, as I said, that we use the like on-shelf radar.
Mhm.
So that has a certain angular resolution limit. So when it crosses, we didn't do any kind of like nullification. Rather, we just use the another technique. It's called ICH8 algorithm based on their like a SNR informations.
Mhm.
So probably yes, you are right. We can also integrate some beam forming as well as super resolution beam steering technique can also help throughout. Yeah, but we
Mhm.
explored like a on-shelf antennas beam width limit, and if it crosses, then we use like another signal processing approach. But
Mhm.
probably, yeah, another thing can also be integrated with the beamforming technique or the angle of arrival technique. Definitely, that's a good solution, I would say.
Thank you. There was an administrative question. I didn't receive the email for today's session. What we did is for the first workshop, we put the registration link. Then we decided to make it open. So the link is shared to join us on Zoom. So you don't really need to register, but when you're attending the workshop, you need to register so you can have attendance certificate. There's another question, till when the quiz is open. I will say the quiz is open for next few weeks. So please try to do as soon as possible. Okay. So with this, I think we are just a few minutes over the time. So let me thank Dr. Islam for a very informative lecture. And thanks to all attendees. Let me just again remind you that this lecture is recorded and it will be available on MTD website, and the quiz link will also be available. Please make sure you complete the quiz as soon as possible. Thank you, everyone. Thanks a lot.
Thank you so much. Bye bye.
Our next workshop will be say next week, same timing. You will be able to see the details on social media, LinkedIn page for MTDYP. Okay, great. Thank you, everyone. Have a good evening and a good day.
Dr. Muzahir, if you let me to have a chat with the MD Islam here,
After this,
and it's just like maybe 1 minute.
sure, please go ahead.
Okay, so
Just
MD
let
Islam.
me stop the recording. So
Okay, please. Yes. Yeah.